This video is about trusses and optimization. Trusses are widely used in mechanical and civil constructions, and our motivation was how to design an efficient truss. That is, if we could, where to put high area and stiffer elements and where to put low area and less stiff elements. And the terminology is the following. This is an element. It's a bar that connects two nodes. And this is the cross-section area of the element. The higher the cross-section area, the stiffer the element. And the truss optimization framework that we are using is a fairly simple one. On the one hand side, we have the volume, or equivalent to the weight, and that's like the cost. And on the other hand side, we have the stiffness, which is the benefit, is how resistant to deformation is our structure for a given load. So the performance is the ratio between the two, is how much stiffness do I get for a given volume. This is a generic truss that we used. It contains 625 elements and at the same time 625 cross-section areas. And for a given load, it will incur in a deformation. So the problem is how to determine the cross-section areas of the 625 elements in order to have a high performance. And this is a complicated problem because it's a high number of variables, and also because it's non-linear relationship between the cross-section areas and the performance. And so the solution that we propose is deep learning. First, we randomly generate a lot of different trusses. In this case, we have a uniform truss, and we use the finite element method to compute the performance. And so we have an X as an input, which is a vector of the 625 cross-section areas, and the performance, and a linear transformation of the performance corresponds to the output. And so this is an example of a randomly generated truss. We have a cluster of high area elements there, and the rest is low area elements. It has a corresponding performance calculated with the finite element method. And this is another example. In this case, we have 3 clusters. Again, a vector of 625 cross-section areas. We use the finite element method to compute the performance, and the output Y is a linear transformation of the performance. This is the distribution. X to the left, we have the minimum, the average, and the maximum cross-section area for every single one of the 625 elements in the truss. And on the right, we have the distribution of performance for all of the more than 45,000 examples. It goes from roughly 0 to 6, and we want the performance to go even further and to be a larger number than that. So our algorithm is a single deep neural network in 2 stages. So in the first stage, we freeze this key layer and we make the main hidden layers learn the relationship between the cross-section areas and the corresponding performance. And here we use the more than 45,000 examples. And in the second stage, we freeze the main hidden layers and we make the key layer learn, specifically the biases. And we make them learn a distribution of 625 cross-section areas. The way we do that is we input a vector of zeros, a single vector of zeros, and we output a single number 1, which is the target performance, which corresponds to the target performance. And so the biases get initialized at 1. This is the visualization of how it starts. And in stage 2, the performance goes up as it goes all the way up to a stabilized number of 9 in epoch 2500. And here we can see the results for 2 trusses of the same volume. The uniform truss has a deformation which is 64% higher than our optimized truss.